and the presenter will be Lhonneur. Is it correct?
Yes.
Okay, and yes, there is a group from France, from IRSN and the University of Montpellier. Please, the floor is yours.
Thank you. Good morning all. So I'm Lhonneur, and I want to present you a study extracted from my PhD, which I have entitled Cement-Based and Cement-Steel Interface Cohesive Parameters Estimates. So my PhD was carried out in the MIST laboratory, which is a joint laboratory between the IRSN, the French Institute for Radio Protection and Nuclear Safety, and the LMGC, the Mechanics and Civil Engineering Laboratory of Montpellier. The MIST laboratory uses and develops a software which is called XPER, and which is able to model crack initiation and propagation on materials using a cohesive volumetric finite element approach. So such an approach consists into dividing a continuous solid media into a multi-body one using a mesh suitable for finite element method. Each finite element is seen as an individual deformable body, which is interacting with the surrounding ones by means of cohesive law. So typically, cohesive law introduces normal and tangential stiffnesses between two adjacent bodies, which may evolve regarding the local stress field by means of a cohesive surface damage variable, which I've called here beta. In addition to the cohesive law in this particular approach, we use the block behavior law in the finite element for modeling volumetric strength. So the general purpose of this study was to assess the cohesive volumetric finite element approach for modeling concrete behavior at a mesoscopic scale, and in particular the concrete made of cement-based matrix and containing steel inclusions. In this presentation I will focus on the pure normal mode behavior, and I will distinguish the cohesive behavior inside the cement paste from the cohesive behavior at the interface between cement and steel inclusions. I will use a particular cohesive law which is called MAL law, and which is implemented in the XPER software. This cohesive law uses 6 parameters: 2 initial normal and tangential stiffnesses, 2 critical stress cohesive stresses, and 2 cohesive energies, so for both normal and tangential opening mode. The initial stiffnesses are not to be estimated as they are not physical parameters, but only numerical ones which are used for calibrating the cohesive model. So to summarize, I focus on the pure normal mode, and the initial stiffnesses are not to be estimated. So at final, only 2 parameters will be of interest in this presentation: the normal mode critical cohesive stresses and the normal mode cohesive energy. So in order to estimate those parameters, I've considered 2 types of samples. The first one, which is a pure cement-based sample containing a notch, and a second one, which is a cement-steel composite sample, both samples measuring 3 cm long and having a cross-section of 1 cm square. I've tested this sample in under 3-point bending tests, as illustrated here. So the cement I used was a same one, 52.5 R with a water cement ratio of 0.5. Steel bars were cutted from steel bars having the desired cross-section. It was a E24S245 steel. Samples were conserved on the lime saturated distilled water for 28 days. And they were immediately tested after having been withdrawn from the conservation bath under frequent bending test with a quasi-static loading up to the sample failure. And we have observed a fragile behavior with a unique crack developing in the sample. So for the cement paste sample, a crack in the middle from the notch, and for the composite sample, an interfacial rupture. So here are the results of the measure of the ultimate strength for both types of samples. As you can see, for the cement paste sample, experiments were more reproducible than it was for the cement steel samples. And for both types of samples, we obtained average value of approximately 140 newtons. In the following, I will construct a practical formula for estimating normal mode cohesive parameters. And for doing so, I will admit the following results. Noting that the first one, which evaluate the ultimate strength considering the normal mode cohesive parameters, may be linked to the Coppard criterion presented this morning by Professor Leguillon. So I have carried out 2D string simulations for both types of samples, 25 for both types, or a total of 50 simulations, in which I choose particular values of cohesive mode parameters close to expected ones, and the resulting data, so the ultimate strength and an average crack speed developing on the sample, have been associated to the used cohesive parameters. So here are the results. You can see in pictures here the ultimate strength as function of the cohesive parameters, and here the average crack speed. So maybe it's difficult to see the values, but you can see that the interpolation proposition here fit quite well the obtained data. In addition, the fitting law here are inversible, and so we can directly obtain the cohesive mode, the cohesive parameters estimates from the data of both the ultimate strength and the average crack speed, which can be measured during experimental tests. So I use these particular expressions for estimating cohesive mode parameters, but unfortunately during my PhD I encountered issues for measuring the crack speed, and so I choose a default value of 130 meters per second as it was obtained in previous study on concrete sample at the centimeter scale. And I use the average value I presented to you of 130 Newton for the ultimate strength. So at last, here are the normal mode cohesive parameters I have estimated for the cement paste bulk and the interface between cement steel. These results may be improved by measuring actual crack speed values. We could think of a similar method also for measuring the tangential mode cohesive opening, the cohesive mode parameter, the tangential mode cohesive parameters. We could use also a similar method for measuring the interfacial behavior between cement paste and other type of materials such as mineral aggregates. And the study of water over cement ratio may be carried out, and at last the confrontation at mesoscopic scale between numerical prediction and experimental measurements may be carried out. So as you can see, it was another study carried out during my PhD. So we obtained first results on this last point. And currently I'm working on multiple fragmentation and material under high-speed loading, so like explosive shock or ballistic impact. And I'm focused right now on the brittle materials. So if you're interested in this topic, I let you my coordinate and enjoy this.
Thank you, Mr. Speaker. So the talk is open to discussion. No questions? Perhaps I will have something. So this is basically the brittle material too.
Yes.
Mostly, even though there is some steel inside. Have you, I don't know, have you tried to analyze it from the point of view of the, because well, fundamentally the final strength is a matter of statistics in brittle materials. So did you try to implement somehow this, or did you see the connection between your simulations and the real results in practice?
Yes. At first we just use average values, but it was a topic I wanted to study during my PhD. And maybe we can see one result. So I've prepared three types of mesoscopic samples with different aggregate localization. And I performed the compressive test. And I compared numerical simulations. So I used the centimetric samples with a supervised test for estimating cohesive parameters, and then I used them on the numerical simulations. Here are the track path observed experimentally. Here is the comparison between the ultimate strength I obtained for the different type of sample, and here is the experimental one. So we can see that we obtain good order of magnitude, but maybe the point in which we have to work is the probabilistic part of the failure mechanism. So here, as the stress field is approximately the same in all the sample, we obtain decohesion everywhere during numerical simulation. In contrast, we can see here that the decohesion is located in a single fracture.
Okay, I see that it is mostly a question of geometry. Actually, you haven't mentioned any role of porosity. So, did you observe anything in this sense? So, because I don't know if you have more pores and how to say, was it so reliable that you always get the same kind of porosity or different, or
I didn't study this point.
Okay, this is probably not so interesting. Okay, any questions? If not, thank you again. So let's move to another talk.